Okay, welcome to this morning's session. Our first speaker is Richard Bergmair. Richard Bergmair is a native Austrian. He comes from Linz, but has been studying in compatriots. He's been studying at the University of Cambridge in UK. It's Cambridge, UK, not Cambridge, Massachusetts. And the talk he's going to give today is basically a report on his master's thesis there. For those who've been into computers for some time, well, you may remember that natural language querying of databases was a big thing back in the late 70s, early 80s, and was then completely swamped by the advent of graphical user interfaces. This was a point when basically interest in those natural language querying issues more or less subsided. Probably also because, well, natural language interfaces are always a difficult thing to do, and it didn't really work out very well back then. But now we're much smarter, and so Richard's topic for today, for the first talk, is a natural language database interface using fuzzy semantics. So, first, one thing, if you've got questions, please use a microphone. There are people watching this via web stream. There'll be people watching this afterwards on video, and they won't understand you if you don't use a microphone. So, Richard.
Thanks for the introduction. Thanks for the introduction. As the chair already said, natural language database interfaces have already been around, but now there are two things that make the situation today very different from what it was in the 70s. One is that database technology has gotten a lot better, and the other is that linguistic front-end processing and linguistic grammars have gotten a lot more broad coverage and a lot more robust. So, as the chair already said, this came out of some work I've done on my MPhil thesis in Cambridge. So I'd first like to thank my supervisor and Copestake. Then I'd like to thank Ulrich Bodenhofer at the Johannes Kepler University in Linz for helping out with the fuzzy logic related bits of this. So he's really been very helpful throughout my work here. And then I'd like to thank Ted Briscoe at Cambridge and Daniel Osherson at Princeton for reading some of the related manuscripts, and thanks to a whole bunch of people for participating in the experiment. What is the overall idea of a natural language database interface? Well, you simply have a natural language expression that you use to state your information need. For example, I'm interested in a hot, dry city, or I'm interested in a large city near San Francisco. And then this can be resolved against a database that actually has data about cities and cities being near others. So what you see up here is a screenshot of a prototype we've actually done, and you can give it an expression like hot, dry city, and it will give you a ranking of records in the database, ranked according to the degree to which those records fulfill our intuition about a hot, dry city. So that means that for the top-ranked cities, we see that they all have very high average year-round temperatures. They all have very low number of wet days in a year, so that is really what we understand as a hot, dry city. And then as you look at the lower ranked records, you see that temperatures tend to decrease, number of wet days tend to increase. So this is really the intuition. This sort of ranking is what we want to have if we're interested in a hot, dry city. So how does all of this work? Well, the basic assumption we make here is that there is natural correspondence between the way we define a data model and the words we use in natural language to refer to certain objects in the data model. For example, we can have a table. That table is place, and we use a noun like city to refer to a record in that table. So for every record, we will have attributes like name, so we can use an identifier like San Francisco, and that turns into a lexical item. So when we say San Francisco, we actually address a specific record within that table. And then you can have a population attribute, so that population will turn into an adjective that's like a big city, a small city, a dry city, a rainy city. So there will always be measurements that you can use to determine those. And then you have, for example, of course, those entities enter into relations. So those relations are, again, represented by tables. For example, you can have the distance between two places. So an attribute of that will be the number of kilometers between those two cities. And then you use words like near and far from. So I'm interested in a city near San Francisco, stuff like that. So from a linguistic point of view, what we're really interested in is we have an expression like a small city near San Francisco. And then, of course, if small turns into a logical predicate, like small of x, where we know that x is a city, and the question is, what does small of x really mean in terms of the population of x? What does near prime of x and y mean in terms of the distance between x and y? So in linguistic, that problem is known as vagueness, and it's involved in determining the meaning of stuff like small and near. Now, before I go into all of the detail of how this works, let me just tell you where I'm coming from with this. The reason why I'm speaking to the hacker community today is because I'd really like to see some technology transfer happen here, and I'd like to see this technology transferred into open source projects and stuff like that. So what you see up here is a screenshot from what is actually a scientific prototype. And there's nothing wrong with that prototype, but its purpose is simply to demonstrate some of the points I had to make in my thesis and to bring to a proof of concept the sort of software I was envisioning. But the software I actually have is far from a sophisticated software package that you can just use out of the box to do something nearly useful. So if you're sitting here today and you say, well, this is kind of too cool technology, I'd really like to start an open source project or something like that to make this kind of stuff happen and to make a useful piece of software out of that, then I'd really like to encourage you to come and see me afterward. So I think there can be no greater success for me for this talk here than inspiring some of you guys to go out and do useful and cool stuff with this. But what I will talk about right now is, first of all, putting fuzzy semantics to use in a closed domain question answering system. So I'll give you all of the broad ideas about how to construct this natural language database interface. Then I'll talk about vagueness and fuzzy semantics, sort of the linguistic background that we need in order to determine whether or not what we're doing here makes any sense. And then I'll take a step back and talk about fuzzy logic as a generalization of bivalent logic, which is gave rise to this nice subtitle that what I want to do is, wild speculation about the nature of truth and other equally unscientific endeavors. So the first thing we will get rid of in terms of science is the assumption of the excluded middle in logic. So in a classical bivalent logic, we say that A, such as, for example, the set of all small cities, is a set on the domain of all cities if and only if there is a characteristic function mapping a certain city to zero if x is not a small city, and mapping x to 1 if x is a small city. So there can only be two truth values, 0 and 1, and there's nothing in between. But that's not naturally what we're doing, right? Naturally what we have is a continuous measurement here, such as the population of a city. And then all we can do with this sort of model is we have to define a threshold. So we can say that maybe we consider every city with population up to 30,000 a small city. So that means that a city with 29,999 population is definitely a small city. So we can come up with an SQL statement that says, like, select star from place where population is smaller than 30,000, and a 29,999 population city will be in that result set. But a 30,001 population city will not be in that result set. And this sort of discontinuous behavior is actually what we don't want. So in fuzzy logic, we make another assumption in terms of the logic, which is that there are infinitely many truth values in the unit interval. Not only 0 and 1 can be a truth value, but every value in between 0 and 1 can also be a truth value. And that means that we can make a more realistic assumption here, and we can say that every city with population up to, I don't know, 10,000 is perfectly matches our prototype of a small city, and then every city with population over 1 million or so is definitely not a small city anymore. And in between, we do some kind of linear interpolation. So if we have a city with population 70,000, then maybe that's a small city to degree 0.7 or something like that, where that degree doesn't really matter all that much in itself. But the point is that we can use those degrees to actually rank those records. So we can come up with a ranking of cities ranked according to the degree to which they are small cities. And this actually naturally maps into stuff that you can actually observe in the way people use language. So what we've done here is we've asked 20 people about buildings. So if a building is built in 1960, is that an old building, yes or no? So we asked that 20 people, and we see that for the question, I don't know, 1940, there's very high agreement about the fact that, yes, this is an old building. And then as you approach 1975 or so, there is minimal agreement about whether or not a building built in 1975 is still an old building or already a new one or whatever. And then the function rises again. You get higher agreement again for 1995 or so, when there is reasonable agreement again that a building built in 1995 would have to be would not be called an old building anymore. So this is the agreement we observe in the way language is used, and this naturally translates into a characteristic function like this. And the idea of this characteristic function is that you give it the year in which a building was built, an attribute that you can actually have in the database, and it will return the degree of oldness of that city, the degree to which something matches our idea of being an old building. So that means you can take a natural language expression like hot, dry city and directly translate it into a select statement that looks like this. So this thing is what linguists call an n-bar phrase or a noun phrase in a way without the determiner. So the idea is that you have a noun in there, city, and that noun actually tells you that you're looking at a place table. So I'll tell you how we define that mapping later, but the point is there is this mapping. So you select an entity x, and that's from the place table, and then x will have a temperature attribute, a rainfall attribute. So you plug the temperature into the degree of into the characteristic function for hot. You plug the rainfall into the characteristic function for dry. So and you say that both of these constraints actually have to be fulfilled. So what you're looking at is a conjunction logically. So I'll tell you about how to define this conjunction later. But the point is that using this expression, you can actually select the degree to which x matches our intuition of being a hot, dry city. So you can simply order by that and say that you're only interested in stuff that's actually fulfilled. And then similarly, you can have an expression involving multiple cities. So in that case, we have a city X, a city Y. X is a small city, Y is San Francisco, and X is near Y. So that also translates into an SQL statement, and I'll tell you about the details of how this mapping is done later. The overall architecture of this is that, what's going on now? Okay, the overall architecture is that you start out with what I call a linguistic data model. So that's this guy up here. And then I built a couple of tools to work with that, but let's look at the linguistic data model first. That was the overall idea. So objects in your definition of a data model directly correspond to words and linguistic expressions. And I've come up with a linguistic data modeling language that allows you to actually come up with a data model in that way. So you declare a place here that will directly translate into an SQL table containing data about places. And then the place table will have an attribute latitude, longitude, it will have an attribute temperature. And within those declarations, you also give it lexical entries. So the idea here is that you use a word city to refer to any entity, to any record in the place table. You use words like hot or cold to refer to certain ranges of attribute values for the temperature attribute. And then similarly, you can have an ID. So the idea for our place entity would be a place name. So that could be a string that says San Francisco. And since we do an ID declaration here, the toolset will actually know that this will directly translate into a word. So that if you have San Francisco as a value in any of those attributes, then it will actually give the linguistic grammar a cue to say, okay, San Francisco is now a word in our language. And then you can have references. So in the place table, we will have to reference many other places when saying that one place is near the other. So that will translate into an associative table in SQL that has a primary key on the place, a foreign key on the place, and an attribute distance that tells it what is the distance between those two cities. And we refer to that attribute of distance by saying something like near. So that is this linguistic statement here. So this all starts out by a developer writing down this data model. And the idea of the linguistic data modeling language is really quite central to making this work because as far as the natural language processing stuff is concerned, there is always the issue of AI completeness lurking somewhere in the back. So this is a closed domain setting, and closed domain settings is, I think the best example is probably Shrewdloo, this 1970s robot. You can tell, put the blue pyramid on the red box, and then it will do it. And the idea very much in the 70s was that you can do something like that, have a robot that operates in a micro-world domain like the blocks world, and then those ideas will naturally scale into a real-world domain. But this scaling doesn't work because there's a knowledge engineering bottleneck there that in practice we can't really overcome. So what I've done here in terms of my tool set is none of my tools involve anything about places or distances or cities or buildings or whatever. It's really just general code that you can parameterize using the linguistic data model. So although my examples all involve this example domain is really defined by a 100-line linguistic data model. And if you give me any other data model, then I can use my tools to come up with a database interface for any other data model as a matter of hours or so. So this is basically a closed domain approach, but you can very straightforwardly and rapidly declare the sort of domain that you're interested in. So you start out by declaring this domain that you're interested in, by coming up with a linguistic data model, by writing this sort of crap. And you feed it into this LDM tool, which is a little Python script that I've written. And that LDM tool will generate a lexicon. So remember, we had the problem of San Francisco appearing in the database. So at this point, San Francisco will get translated into a lexical item, and that lexicon plugs into a grammar. That grammar is the English resource grammar. Credits for that go to Dan Flickinger at Stanford and a whole bunch of other people. And then that resource grammar can be run in a runtime environment, like the Linguistic Knowledge Builder, LKB. Now, this is a tool that has been written by my supervisor, Ann Copestake. So all of this is basically automatically generated, and then you get the natural language database interface. And this database interface can take a natural language expression, hot, dry city near San Francisco, plug it into the LKB. The LKB uses all of this linguistic knowledge to return a logical form. And that logical form could look like this. So this is actually a quite non-trivial problem. And if you were doing natural language processing back in the 70s, you didn't have a broad coverage grammar like the ERG, and you didn't have an LKB that does all of this work for you. But nowadays, this stuff is pretty robust and pretty broad coverage, so you can just more or less use it out of the box. And you give it an expression, dry city near a rainy city, and the LKB will automatically figure out what sort of entities are involved in this. So there are two things involved, x1 and x2. x1 is a city, x2 is a city. x1 is dry, x2 is rainy, and x1 is near x2. So that's very straightforward, this logical form. And we see that this naturally translates into what we have in the SQL statement. So x1 is dry, x2 is rainy, so this is basically just the same expression. And then by looking at the nouns, you know what tables you have to select from. And this correspondence now, obviously it comes from the linguistic data model, because in the linguistic data model we said that for the place entity you get the city noun to refer to it. So that way you get the correspondence worked out. So you get a statement from the user. The user is interested in a hot, dry city. That goes into the LQB. LQB returns a logical form. That logical form is translated into an SQL statement. The SQL statement is run against the database. That gives you some data, and the data is returned to the user. But there's one more aspect to this, which is that you have these characteristic functions, dry, near, rainy, stuff like that. So you have to work out what does dry mean in terms of the average rainfall in a city and so on. And this really leads into the linguistic part of this talk. And what we're interested in here is designing an experiment. So what we do is we ask yes-no questions to a couple of subjects. So if a city had a year-round average temperature of 12 degrees Celsius, it would be natural to call it a cold city, yes or no. If a skyscraper had 78th floor, it would be natural to call it a rather tall skyscraper, yes or no. And the way we ask these questions is sort of reminiscent of the game where someone thinks of a number in a certain range and the other person has to guess what the number is. So, of course, the way you do this is you do a binary search and you find the value. So, first of all, we ask a person with 0 hair, would that person be considered bald, yes or no? Well, of course, a person with 0 hair is bald. A person with 1 million hair, is that person considered bald? Well, no. A person with 500,000 hair, is that considered bald? Yes or no? And then by asking those questions in a binary search fashion, you find two neighboring values in your data set that are actually answered with different answers, and then that gives you one decision boundary. So you do that for one person, and you find out where does that person draw the line between baldness and not baldness. And of course, that one decision boundary is not very meaningful in itself. But you do that with 20 persons, and then you can look at the distribution of how this works, and you can come up with the agreement function that I've shown you earlier, and from that agreement, you can determine the characteristic function. So let me just show you that slide once more. Yeah, so remember we ask about the decision boundaries, and then using those decision boundaries, we get the agreement between those 20 people. And then this agreement corresponds to the characteristic function in this way. Now, of course, the data we collected by doing this with 20 people was also used to test our linguistic presuppositions we made. So it turns out that actually it works pretty well. So people place the decision boundary for tiny cities very low on the population scale. For huge cities, we get very high values. For big and small cities, we sort of get the same values, which is exactly what we expect. Because as soon as people don't call something a small city, they start calling it a big city then. And at least this is what this data looks like. And then, for example, we gave them the number of kilometers between two cities and asked them about whether that's near. So you get reasonable scatter here, but you still get a nice value here, and you still know that, well, if there are 300 kilometers between two cities, then no one calls those cities near. So another thing we did was we gave them the year-round average temperature in a city, and we asked whether the city would be a cold or a hot city. We gave them the average rainfall and asked about whether it's a dry or a rainy city. We gave them, this was another domain, the skyscrapers domain. So in that case, we asked about the number of floors a building has and whether it's a small or a big skyscraper. The completion dates, and ask about whether it's an old or a new skyscraper, and so on. But the cool thing about this is that you can actually come up with this experiment without doing any additional efforts, because of course for doing the experiment you ideally want to have some sort of nice web interface that people can go to, and then they click on yes or no a couple of times, and then you get that. And this is automatically generated using these description entries. So if you talk about the temperature, then in the linguistic data model you can also specify this question. So if a city had a year-round average temperature of blah, so this gets replaced by some actual temperature value, degrees Celsius, it would be natural to call it a such and such city. And this such and such is actually resolved using these generator entries, which basically act as a context-free grammar. So this is all automatically generated. So remember, we were talking about the natural language database interface. We have a couple of experimental subjects here. So the experiment is automatically generated from the linguistic data model and from the database. Then the experiment is done by a couple of experimental subjects. What we get is those characteristic functions, which are these nice tools for translating a temperature into a degree of hotness. So that's generated here, and then the natural language database interface can use that. So in terms of the linguistic theory that we have about this, what can we say from our data? Well, first of all, membership can clearly be judged as non-increasing or non-decreasing. So if you ask about a vague statement like bald, then you always get the situation where someone with 0 hair is bald, someone with 1 million hair is not bald. You never get the situation where someone with 0 hair is bald, someone with 100 hair is not bald, and someone with 200 hair is bald again. So a function will never have a shape like this. It will always go like this or like this. And then the second thing is that in that function there will be a region of fuzzy membership, so that there are a couple of values for which there is no dispute about whether that is a bald person or not. So you will have a transition region somewhere in there. And the way we tested that was to look at different values for cutoff points, and then if you define a certain cutoff point for the agreement that you want, you still get a certain portion of points in your data where you have the agreement you want, and similarly, if you say you want to have a certain portion that have high agreement, then what is the maximum agreement that you get outside that region? So this means that this is pretty consistent with our observations for some, but not quite all of the data. So there was some stupid mistakes we made. We asked people about rainy cities, and in the sample we had cities from California, which of course don't really contain very good examples of extremely rainy cities. And actually we've done the experiment with British subjects that have sort of different standards. But yeah, this is the sort of stuff that we can actually fix. And by looking at the data, it was actually pretty cool to see that our method pointed out the places where we made mistakes. So it seems I'm pretty optimistic that we're on the right track here. And by reiterating the experiment, we'll be able to get some decent data. So yeah, another thing was that decision boundaries can be contradictory across speakers, but they're never contradictory within a speaker. So that some people call something a small city, a tiny city, that other people wouldn't even call a small city. But you never get one person calling a city tiny that's actually larger than a city they've already called small. So this led us to adopt this approach of ordering-based semantics. What is this all about? Well, instead of taking the actual values, we're only interested in the rankings. And the rankings are actually quite robust in terms of the values. So if you look at the decision boundaries, there is no need for the decision boundaries to agree in order to ensure that the rankings agree. So in terms of the linguistic theory, you have speaker and hero. You give speaker the city X, and X has 123,729 population. So to what degree is X a small city? So you ask two people, and they will give you a different degree. That's almost for sure. But you ask both of these people to rank a number of cities according to the degree to which they are small cities, then you will most likely get the same ranking. So those rankings are pretty robust. So we see that for these two characteristic functions, the decision boundaries don't coincide, but at the same time, the rankings do coincide, because whenever there is a value that's smaller here than another value, then it's also the case for the other function. Okay, my talk has been going on for 30 minutes, which is why I will now give you a Dilbert episode. Okay, do I have your attention again? We will come to questions later. So let me just give you a summary once again. We're doing a natural language database interface. What we want to do is we have a natural language expression. We're interested in all hot, dry cities. And then I came up with this prototype, and that actually ranks all the records in our database according to the degree to which those records fulfill our intuition about something being a hot, dry city. So we get records with high rankings that have high temperatures and low number of wet days, and then you get the right rankings. This is possible by saying that there is a natural correspondence between the way we define a data model, the sort of objects we have in a data model, like tables, and lexical types like nouns. So you use a noun like city to refer to a record in a place table. You use an adjective like small or big to refer to a certain range of values in a certain attribute. And this is done by actually specifying a linguistic data model in a linguistic data modeling language that I've come up with. So this will plug some linguistic information into a grammar, and then our natural language database interface can use that grammar to take any expression like hot, dry city, plug it into the linguistic knowledge base, get back a logical form, plug that logical form into an SQL statement, run that statement against the database, and return the data to the user. And now comes the philosophical part of the talk, which is we will talk about fuzzy logic as a generalization of bivalent logic. And looking at these logical things, it really, for me, this was a great eye-opener about the way logic in general works, and about what sort of models you can actually build with logic. So in fuzzy logic, we need a conjunction operator that actually was involved in our SQL statements. And the way a conjunction is defined in fuzzy logic is to say that any operation on the unit interval can be a fuzzy conjunction as long as it's commutative, associative, just like a normal conjunction, as long as it's non-decreasing and has one as a neutral element. So those two basically boil down to saying that a conjunction can never be any truer than any of its conjuncts. And actually, psychologically, this is a sort of interesting question, because psychologists have been looking at what they call the conjunction fallacy for quite some time now. So what a psychologist will do to find out intuitively what people are doing when they're trying to come up with conjunctions is they give people, for example, a story about Mary. And then they ask them, is Mary a secretary? Is Mary likely to be a rich secretary or something? And then you get people thinking that it's more likely that Mary is a rich secretary than that Mary is a secretary. So in terms of probabilities, of course, this mathematically doesn't really work out, but there is a very interesting field to this in psychology in trying to find out how people deal with logic intuitively, as opposed to the way we do it in mathematics, where we just come up with a couple of with a couple of definitions. So, but nevertheless, for fuzzy logic, this is the way a conjunction is defined, and it tends to work out pretty well, and it tends to correspond to what humans do not too badly. Although the psychological elements, again, this is something that is very different here from the 70s approach to artificial intelligence. Because in the 70s, people said, we can simulate what a human brain does, we can have a computer do anything that a human can do. But simulating what a brain does in a computer is actually something that no one really believes can be done nowadays. So in the 70s, this was the approach. Nowadays, this isn't the approach. So we kind of just took the engineering approach, made a couple of definitions, and see whether it works out. So the standard triangular norms that are often used in fuzzy logic is you do a minimum, for example. So you have proposition P, which is true to degree 0.8. Q is true to degree 0.5. And then the conjunction P and Q is true to degree 0.5 if you use the minimum, because that's the smaller value. Or you could do a numeric product, so that would make it true to degree 0.4. You can do this Lukasiewicz T-norm, or you can use a drastic product. So those are all sorts of definitions that you can do. This is more or less the standard definition, which is to say that the conjunction is defined by minimum, and the negation is defined by this standard negation that says that P is true to degree 0.8, then not P is true to degree 0.2. And then, of course, if you have an AND operator and a NOT operator, that will give you a full logic. And this logic is called a Gödel logic in that case. Or you can use products here, then you get a product logic or a Lukasiewicz logic or whatever. So the cool thing about logic is that it underlies pretty much anything. But for computational theories, it gives you nice generalizations over what's going on. So think about a finite state automaton. You have a number of states that are interconnected, and you can make a transition from one state to the other state. And then any state can accept a certain number of symbols or not accept them. So then you say that a certain string is in the language defined by that automaton. If it fulfills the requirement that the first state accepts the first symbol, and you make this transition, and the second state accepts this symbol, and you make this transition, or you make this transition, and the second state accepts this symbol and the second. So this whole thing is just a big disjunction of conjunctions. It's just a disjunctive normal form. So usually this is done using a normal bivalent logic, of course, which is sort of boring. So by using fuzzy logic, you can stick any triangular conorm here and any triangular norm here. And of course, doing this thing with the regular automaton and having numbers between 0 and 1 is actually kind of familiar, because we do that with Markov models. All of you who have ever heard of Markov models will probably have seen this this statement before, where we plug a product here and a sum here, and we compute the likelihood of our Markov model accepting a certain expression in the language. So this likelihood can be determined using a forward algorithm, and this forward algorithm will actually compute exactly the value of this statement. So it will compute the product here and the sum here. And we can also do a Viterbi approximation here, which is a bit faster. So and that will put a maximum here instead of a sum. But now we see that the sum and the maximum are actually just two different triangular conorms, and the product is just a triangular norm. So you can actually put any sort of logical statement here and see if this works. So basically, this fuzzy logic stuff gives you a nice generalization over pretty much all of computational theory, and not just the linguistic stuff. which is sort of neat. But for the language modeling problem in particular, again, you can actually induce fuzzy context-free grammars from corpora. So remember the talk yesterday by Dan Kaminsky? He trained this context-free grammar on a certain file to see what's actually going on in the file and to find out about what the syntax of this file is and what the protocol looks like and stuff like that. So he does that using normal context-free grammars. And using fuzzy context-free grammars, you can actually do the same stuff but have a sort of degree of match between symbols and stuff like that. So it's a nice generalization of a normal context-free grammars. But for really working out syntax, there isn't too much point in using fuzzy logic. What fuzzy logic is really cut out to do is doing semantics. Because in semantics, you could say that, well, this sort of seems like probability theory to me, isn't it? You have these values between 0 and 1, and you want to have a conjunction, then you multiply them and stuff like that. Isn't that probability theory? Well, actually, no, it's not. Because if you're looking at bald, and you say that bald of x is a probability density function, then what probability theory is all about is dealing with uncertainty. And uncertainty is mathematically very different from vagueness. Because if you have perfect certainty, if you know that there are exactly 76,273 hair on a person's head, and you want to ask the question whether that person is bald, and you plug that value into a probability density function, well, then the probability will be 0. You will maybe never have observed a person with exactly that many hair, and therefore, probabilistically, you can't say whether that person is bald or not. So what's, of course, done in probability theory is that you define confidence intervals and look at probabilities of something to lie in a confidence interval and stuff like that. But it doesn't really make sense for fuzzy semantics because how would you define those confidence intervals? And the other thing is that in probability theory, you need an independence assumption for a conjunction. So you flip a coin, the probability that it turns up heads is exactly 0.5. You flip a coin twice, the probability that it comes up heads twice is 0.5 times 0.5. Doesn't that look like a fuzzy conjunction? Well, no, because a conjunction is something logic, whereas a probability looks at event spaces. So that means that if the first event of throwing the coin for the first time and then the second event of throwing the same coin for the second time are completely independent, then you can do the conjunction, the probability of the co-occurrence actually by working out the product. But you can't do that if the events are correlated in some way. And actually doing logic on events means that you're already assuming that there is some sort of relationship between them. And that means that it doesn't really make sense to make an independence assumption here. So what's different between probability theory and fuzzy logic is that fuzzy logic is a logic in the sense that it has a truth functionality. The degree of fulfillment of a statement which is composed of other smaller statements is a function of the truth values of those smaller statements. Whereas in probability theory, it's not a function, the probability of, say, a co-occurrence is not a function of the probabilities of the occurrences of the events, but it's a function of what's actually going on. You actually have to look at the events and whether they are independent and justify those assumptions. And those assumptions tend to be really hard to justify for doing linguistic stuff. So this is the theoretic part of the talk, which then concludes the whole thing. And at this point, I want to remind you once again that why I'm standing here is because I really want to inspire some of you guys to go away and maybe do some technology transfer and maybe employ this kind of stuff in a useful way. So if at any time during this talk you've said to yourself, wow, this sounds like fun, I can think of a cool application where I can plug this stuff in, then please do feel free to come and see me afterwards, and I'll be happy to collaborate with any of you on cool projects involving this kind of stuff. So at this point, I'll say thanks for your attention, and I'll be happy to answer any questions.
Well, thanks, Richard. There was a question back there quite a while ago.
One thing that came to mind was search engines for the internet. But I'm not sure if it really fits, because in your examples at least, the domain was always very well defined. You said we had one domain, skyscrapers, and the other domain was cities. And as a result, you can get the non-contradiction within one person. That is one thing you pointed out. If you ask one person, is a city big or small, it does not contradict itself on a scale of the largeness of the city, of the population. But if you're not certain that the two questions rely to the same domain, this does not hold any longer.
Yeah, exactly. So in linguistics in general, or in computational linguistics, one of the very basic distinctions that is made is between open domain stuff and closed domain stuff. So this is closed domain in the sense that we relate a linguistic expression to a certain model. So the model defines our meaning, and we want to find out the meaning of the expression by drawing the connections there. And the open domain stuff, like with internet search engines, or all of the stuff that doesn't need any knowledge about what's going on, doesn't work by relating the expression to a model, but relating expressions to each other. So what Google does is you give it a query, you give it your information need in natural language, and it has these web pages out there which are also written in natural language. So there is no point at which Google actually understands your information need. All Google does is that it matches the query to the document. So I'm actually working right now. So this was my master's thesis, and I now go on to do PhD. And what I'm doing now is that I try to translate this stuff to the open domain setting, in which we try to use the fuzzy logic and the fuzzy semantics ideas to come up with a good way of comparing documents, or comparing a query to a document in an open domain way. But this is sort of non-trivial. We can talk about my approaches to doing this afterwards, but for this work, it's very much outside the scope.
I think that regarding, again, internet and Google, that if you train your audience how to put a query, then you can use Google's indexing system so that it's easier to find out the fuzzy logic answer for the queries, point one. And Jimmy Wales, the founder of Wikipedia, is now starting a new search engine called, now I don't remember. And anyway, so he wants the work of every user put inside, so they shall check whether the ranking of the answers are good or not, relevant or not. So, and with these answers, he hopes that the ranking shall be better. So maybe this is also useful advice so that people can make an input into the ranking, and so maybe then not by fuzzy logic, but by what was this? Picking up a coin.
Yeah, probability theory.
Yeah, probability. So maybe with these two methods, it helps to refine your answers. Thank you.
Yeah, with probability, it's. I mean, part of the whole business of doing search engines is that you don't only have the linguistic criterion of how well does the query match the content of a web page. You also have an a priori criterion of how good is a web page in itself. So there are web pages out there which are just crap, and there's no way that anyone could be interested in anything that's on there. And the way Google does this is of course by doing PageRank and by giving it PageRank scores by looking at how the pages are linked to each other. And this is not always the case for doing linguistic stuff. And then another part of doing the search engine stuff is that you very much have to worry about what your index looks like and whether you can quickly search the index and whether your index supports all the search functions that you want to do. If you look at those logical forms, then you will see that the logical forms actually more or less add information into what's described, and the logical forms will actually take more space than the actual web page. So if you imagine that Google wants to do this, this means they would have to have an index that's larger than the web itself, which is definitely one of the I mean, Google has a lot of money, but seriously, they can't do this. Yeah, it's very much about search engine technology is, from a linguistic point of view, still very far from what can be done in terms of really understanding stuff in a natural language processing kind of way. And this is due to some inherent restrictions of building search engines. So this is not the primary target that I see for this kind of technology.
Okay, back question to the adjectives. If there are some unknown adjectives in the query, is it possible to ask the user back, what do you mean with hot city or with snowy city? I don't know. Is there some approaches?
Yeah, from the general idea, if you have multiple ways of defining, for example, a big city could be defined in terms of the population of the city, in terms of the area of the city, or maybe in terms of the average number of Starbucks per square meter. So if you want to disambiguate this kind of stuff, then naturally what you would do is you would just put 3 lexical entries with the same word in the model, and that will give you an ambiguity. And the way you resolve this ambiguity could be by asking, for example, the user. But we've not done this for one reason, is because we argue that, first of all, we don't really need it for the proof of concept kind of deal we're doing. And the other thing is that we make the assumption that people will naturally assume a frame of reference or whatever. So you give them the experiment and you ask them, a city with population such and such, is that big or not? So people will automatically make certain assumptions about what you mean by big. And then by collecting the data in such a way, that means that at the end of the day in the natural language database interface, the computer will make the same sort of assumptions that the human users have done. So asking back is definitely a possibility, but it is not something that we've directly implemented here.
I have a question put in between. One problem with natural language processing in open source is that usually the linguistic resources are published under, well, if they are published at all, then the licenses are just crazy. So you basically can't do much with the linguistic resources. Now, you've mentioned this LRG, or what it was.
Yeah, exactly.
What license is it under?
Yeah, so as I've said, the ERG, including its lexicon and everything else, is... so this all came out of an EU project, actually, at some point. Or it was an older project, and then at one point it was converted into an EU project. Anyway, it's called Delphin. So the URL is www.delph-in.net. And I think it's cited in my paper linked to this anyway. So this was done by Stanford, and it's open source in the sense that it's redistributed under the LGPL. So you can just plug it into any sort of open source software that you want to do. You can even plug it into commercial software. And the same thing goes for the LKB. Now, the LKB is also distributed freely under the LGPL, but one thing you have to be aware of is that it's written in Lisp. Not my idea.
I have a question. Is it possible to use such a database to understand, in quotation marks, text? For example, if you read law text, there it's written, for example, if you do this, then you will be punished with that. Or if somebody does this, the consequences will be that. And thousands of hyperlinks. So because they say, look in paragraph something, and and you have to check this and this. So is it possible to put all this text into a database and to do some data mining so that a normal person can understand law text? So for example, if you bought something, you will know. You want to know, do I have a possibility to get my money back or something? So you put in the question into the machine, and it does something, and then you have a possibility, because it's fuzzy, from maybe 80% that you get your money back because of paragraph something, and then you get the report, go to your dealer and say, the chances are very good to get my money back.
Yeah, so what I've done in this work is that I've assumed the database is kind of there, and there can be a knowledge base like in between the database and the question answering stuff. Now your question relates to, you have this text of law, and now how do you understand the law and put it into the database? So that's sort of the other way around. And this is actually handled under the name information extraction. So there has been work going on in that field for quite some time now. And it's about extracting ontological relationships. So if you're talking about law, then one of the stereotypical relationship can be like a cause-effect or a situation-punishment type of tuple. And there is some very interesting work on this using the same linguistic infrastructure that's available on LGPL. That's done by Aurélie Herbelot. So if you look at the webpage describing this talk, there is a link to the natural language group at Cambridge, and Aurélie Herbelot is a PhD student doing work on information extraction particularly.
And how good is it?
If you ask the question, how good is it, then the primary resource is TREC, the Text Retrieval Conference. And that's a conference that's done once a year, and it does competitive evaluation. So it gives people one interface saying that this is what a program looks like that does information extraction. And then they go out and collect all sorts of data, like they have poor humans sitting there for weeks, all day long, tagging that, okay, there is, in this piece of text, we have this relationship, and then we have this relationship. And then you get a whole sort of data, and then you let the computer do the same thing, and you look at whether stuff matches. So they do that competitively, so research groups around the world submit their programs, and then they look at what sort of percentage agreement you get. So if you just Google for TREC, T-R-E-C, then you will get the results for the last year, and you can look at what the evaluation was like and what the sort of numbers they got.
And how far is the way to have such a lawyer for open source lawyer that does not cost something?
I think that's probably an AI complete problem, actually. So if you can build the open source lawyer, you can probably build hell. But on a more shallow level, there's a lot of stuff that you can do to support people in, to support lawyers to do their work more easily, or in our case, to support just smart people like hackers in educating themselves about law and, you know, surfing the law in an efficient way and doing certain stuff automatically. But the other thing you always have to be aware of in terms of law is that law doesn't work like code, in terms of there is a logical, a chain of deduction that leads you from the axioms of law to the fact that I, Richard Bergmair, can crown myself as king or whatever. So, law is interpreted by judges in a sort of intuitive, human way. It is fuzzy.
I have a comment and a question. The comment was that, as you pointed out, what's raining in Britain is not what's raining in California. So maybe another development could be adding maybe different functions for the same term, depending on who the user is, so on user groups maybe. But the question was, can you do that in other languages in practice? So in terms of availability, for example, of a grammar, is there anything like a ERG in German or Italian or French?
I think there have been efforts to come up with. I'm pretty sure there is a grammar out there. It's done at the University of Saarbrücken, the University des Saarlandes. And this is a German grammar that's done in the same formalism, so you can run it in the same runtime environment. And then there is also Japanese grammar. And I think there are modest first stages of doing a Spanish grammar or something like that. But yeah, generally there are grammars out there for most languages. Most of them are not quite as sophisticated as the English grammar, so most of the work goes into English right now. But there is stuff out there, especially for German. There is actually pretty good stuff, and for most other languages, there is at least some ongoing efforts to support that. But this is why I said that the situation is different nowadays from the 70s, in that we have this sort of linguistic resources about English now. And of course, this is an effort that takes quite a while, and so maybe chances for doing stuff other than English are a bit slim right now. So I think the most rewarding language to work on is English, plus Arabic, because there's a lot of money being put into Arabic right now for reasons that I wouldn't want to comment on. But yeah.
Well, we have time for one last tiny little question.
Thank you. I was considering your closed-domain approach, and it came to my mind that computer programs and the help function inside a computer program is, by definition, a closed domain. Have that been taken into consideration to use this to make better help user help functions in computer programs?
Actually, that's a good idea. I haven't really considered the idea, but it's certainly something that people might want to look into, yeah.
Yeah. Well, that's about it for this talk. Further questions can be addressed to Richard directly. We have a break of a quarter of an hour now, and the next talk will be in this room, Fuzzing the Corporate World, and this is a completely different kind of fuzzing than the fuzzy logic we've heard here. So see you then if you like it. And thanks again, Richard.